In this screencast, we are going to talk about phenol, ethers, and thiols. So we're going to start with phenol. Phenol's a colorless, low melting point solid, and it has a medicinal odor. When you add a small amount of water to phenol, it causes the solid to liquefy at room temperature. And that liquid mixture is sometimes called carbolic acid, right? Now, unlike alcohols, phenols are weak acids, which can damage skin by denaturing the proteins in the skin. And because they're weak acids, they can react with bases to form a salt. And so sometimes we get the salts there as well. These really need to be handled with care. However, in dilute solutions, phenol is used as an antiseptic and a disinfectant. In the late 1800s, Joseph Lister was an English surgeon, and he started using phenol as a hospital antiseptic. And before that time, no antiseptics were really being used, and so very few patients survived even minor surgery because of infections. So this was really one of the first disinfectants. Today, though, there are really effective derivatives that are used as antiseptics instead of phenol that are much less irritating to the skin. Now, these are what we call phenol derivatives, which they contain phenol connected to something else. And so we have O-phenyl phenol because we've got that benzene ring attached to the phenol here. And then we have 2-benzyl 4-chlorophenol. These are ingredients in Lysol. Right, which is a disinfectant that's used for walls and furniture in hospitals and homes. So these are still used as disinfectants. Additionally, phenols are used as antioxidants in food. Now, what they do is they interfere with oxidizing reactions that spoil food. Right? And so you can look on a label, which is BHT here, as added to preserve freshness. And BHT is this phenol derivative here that helps keep any oxidizing agents from happening. These two are really common ones. These are widely used as antioxidants in things like gasoline, lubricating oils, rubber, foods, and packaging materials for foods that might turn rancid. In food or containers used to package food, the amount of these antioxidants is limited to about 200 parts per million, which translates roughly into 0.02%, based on the fat or oil content. I want you to also notice that the industrial nomenclature, the BHA and BHT, is much different than these IUPAC names. It's kind of interesting. Now, let's talk about ethers for just a second. Ethers were introduced at the start of this chapter as compounds whose formula contains an alcohol in the center. Common names for ethers are obtained by naming the two groups attached to the oxygen and then adding the word ether. So I want to show you an example. If we look at this molecule, Okay. We would name this substituent and then put them in alphabetical order. So one is ethyl and one is propyl, and so it would be ethyl, propyl, ether, and we put ether at the end there. If the two groups attached to the oxygen are the same, we use the prefix di. So this would be dimethyl ether. So these are those common names where we've just added the word ether. Now, if we're using the IUPAC system for ethers, the group, one of the groups is called an alkoxy group, and it's the smaller of the two groups. So, for example, if we were to look at this same ether here, we would use the propyl, which is the longest group, as the parent chain. And so what we would call this is 1-ethoxy propane, because the one here is showing, hey, look, this ethoxy group is attached to the first carbon there of propane. Okay. Let's look at one where the prefix wouldn't be 1. So for example, if we had this molecule, okay, we have two groups here. We have this group, which is an ethyl group, and then we have this group, which is the longer one, so that's going to have the bute prefix there. And so what we would do with that longer one is we would count. We would say 1, 2. That's where the oxygen, the ether linkage is for that oxygen. And so we would then name this using that butane parent hydrocarbon name, and then we would say, look, that's 2-ethoxy butane. And so that would be the name of butane there. Trying to think. I'd like to do one other one just because we haven't looked at one maybe with a ring before. So if we looked at this one, all right, there's a benzene ring on this. If we were to name this using common names, that would be methyl would be the first one, because this group here is a methyl. When we come over here, the second group is a phenyl, because we're treating that like a substituent. So this would be methylphenyl ether. If we were using the IUPAC nomenclature, benzene would be the parent hydrocarbon, and so we would just write benzene here, and we would say that's methoxy benzene based on the meth here. When we look at the methoxybenzene, we don't have to give a number because there's only one place that could be. Now, we can also have cyclic ethers. These are found when they have when they have an oxygen in a ring like this. It's referred to as a heterocyclic ring. So this is just a ring that contains atoms other than carbon. So, for example, these are oxygen-containing rings that are cyclic ethers. The two most common ones that we're going to run into are furan and pyran. These we're going to see again in carbohydrates. Contain these type of ring systems, and so that's why I'm introducing it now, because we'll see it again when we go over and we study the carbohydrates. Now let's talk about some of the properties of ethers, right? The oxygen atom of ethers can form hydrogen bonds with water. So ethers are slightly more soluble in water than hydrocarbons, but they're less soluble than alcohols of comparable molecular weight. So they're much less polar than alcohols. they're more soluble than the hydrocarbons. Right? But less soluble than alcohols. They generally have, I want to say one more thing about hydrogen bonding. They hydrogen bond in water because we have oxygen here that can provide the electrons to form the hydrogen bond. They will not hydrogen bond if it's just pure ethers, because there's no hydrogen attached here. So there's no hydrogen to form the bond. The hydrogen of the carbon won't form that bond, right? Now, because of this, they end up with really low boiling points because they can't form hydrogen bonds with each other. And they also have low melting points. Because of the inability to form hydrogen bonds with other ether molecules. The chief big chemical property of ethers is that, like alkanes, they're pretty inert and do not react with most reagents. So if we say something is inert, okay, it's not very reactive. However, they are also, like alkanes, highly flammable. All right. So diethyl ether was used as a anesthetic, as we talked about, but it was eventually discontinued because it was so very, very flammable. And so other things have now come along to replace it. Now, the last kind of group we're going to talk about today are thiols. Thiols are just compounds that contain the SH group. Okay. This a lot of times is referred to as a sulfhydryl group, right? And that's just the SH functional group. Now, sulfur and oxygen belong to the same group on the periodic table, so they're going to form kind of similar compounds. So where you see, for example, if this was an alcohol, there would be an OH. Sulfur bonds the same way with 2 bonds and 2 lone pairs here. When we look at this, I want to point out that thiol, an older name for these, are called mercaptans. Right? And the most distinguishing characteristic of thiols is they smell bad. For example, there's ethane thiol, which is added to natural gas, and that's CH3, CH2SH. And the way we name thiols is we just put the thiol word at the end of the name, basically. And so you can see here where thiol has been named. Propane thiol is CH3, CH2, CH2SH. That's the odor in onions. These molecules here at the bottom are all associated with the odor in skunks. So again, these are very, very smelly compounds. Now, let's talk about some common thiol reactions. So when thiols undergo oxidation, they form disulfide linkages. And a disulfide linkage is just where you have two sulfurs that are linked together with R groups on either side, and that's called a disulfide. This is structurally important for some proteins. So for example, how this could be shown is CH3SH plus CH3SH, right? Undergoes oxidation, so we're going to put the O there to give CH3SSCH3. Another common reaction is a reduction reaction, which reduction is the opposite of oxidation. So oxidation can be reversed with a reducing agent. The one that we've learned about is H2, but there are other reducing agents, and I wanted to show you where an example of where we see this used. And where we see this used is in the cosmetics industry with like hair straightening. So if you have naturally curly hair, your disulfide linkages are what give you naturally curly hair or really straight hair. And so when there's a perm or a straightening, what happens is the first chemical that's put onto the hair will reduce those disulfide bonds. And so the one that's used often is a thioglycolate, but that works just like H2 would. And so now the sulfurs have all the hydrogens, and then you either straighten it, or if you're getting a perm and you want curly hair, then you put it on the rollers. And then hydrogen peroxide, which is a common oxidation agent, is added back on the hair, and now it takes the shape of however the position of the hair was at the time that that was applied. So this is used in perms and straightening treatments in hair salons quite frequently. Another place that we see this is that thiols will react with heavy metals like lead and mercury, and they'll form insoluble compounds. This is a generic reaction shown here. A common reaction would be, for example, if you had CH3SH plus CH3SH reacting with mercury 2+. What happens is that thiol forms a bond with the mercury and links like this, and you have a lot of enzymes in your body that contain this SH functional group. And so when the mercury binds, it makes it so that the enzymes can't work anymore. And so that's one of the reasons that mercury is poisonous, is because it messes up your enzymes and they can't function in your biological reactions. And we'll look at that more in chapter 20. The end of this chapter talks a little bit about polyfunctional compounds. These are just compounds with two or more functional groups. An example of this is glucose, which is a carbohydrate. There's an aldehyde functional group here and an alcohol functional group here. And functional groups, of course, help us determine the chemical properties of compounds. And so we talked about cholesterol at the beginning, and it's important to note that cholesterol has two functional groups. We have the alcohol functional group here and the alkene functional group here. And, right, cholesterol should exhibit the reactions, or should participate in the reactions of both alkenes and alcohols because it contains both of those functional groups. So again, these functional groups really drive our understanding of chemical reactions, and we use these functional groups to group together molecules so that we can see what type of chemical reactions they can undergo. So that concludes us delving into chapter 13. In the next chapter, we are going to look at aldehydes and ketones. As always, if you have any questions, please feel free to pop by my office.